Short little tutorial and video about, well, I don't know about this is short, we'll see how it goes, of doing some analyses of a two-stage op-amp. This one happens to be a NPN stage, NPN differential pair stage. All right, so you see my zoom level. I'm going to hit the space bar, which is zoom to fit. It's really nice. It's under my left thumb. Okay, so these analyses and such down here, what I really want to do is the very first task before you do anything is to make sure that your DC solution is going to be okay. All right, so when we want a DC solution for this, we're going to assume that the input plus and the input minus, which is A and B, A and B, A is input plus, B is input minus. This is kind of a normal thing. You have to be careful with the way you do the signs, because input plus means that if this node plus is higher than the minus node, then you have a positive input. You would expect the output to go positive or go up in that case. If it doesn't, then you have your labels wrong. It's just as simple as that. All right, so what we need to do, our analysis first needs to do a .op or a DC simulation. So you see I'm replacing these with a semicolon. Semicolon is a comment character. Control M, or not Control M, Control Enter gives me another line here. I'm going to say .op. The only LTspice can only do one simulation at a time, so that's why these others are commented out. You could also use a star character. A star character as a what's it called? A comment character, but this is what we got. All right, control and then .op. That's an operating point. We have some measurements over here. We're going to ignore those for a minute. This is commented out as you see. Before we hit run, I have two places in this. I have my cute little bias generator circuit, and this allows me to generate the voltages here, bias P and bias N, that correspond to this bias current. You see that over here in the tail current of my differential pair Q5, that we need a bias voltage here for the base emitter voltage. What I really want is a certain collector current for Q5, which then we call the tail current. To generate that nicely, I could put a constant current source here, but that's really gonna that works great for small signal analysis, but sometimes it can get us into trouble, because in a circuit simulator, if I say an ideal constant current source, that current is going to flow between those two nodes no matter what, even if it's bogus. And I don't like bogus, because the whole reason we do a circuit simulation is so we don't have to build it and measure it, and so we can do some work and experiments on that without measuring it. The time that we're in right now, it's a little, I'm not even in my lab, I'm in somewhere else with this COVID-19 stuff. Alright, so this is a cheap little thing. We have a current source, and we have a diode connected transistor. What's important here, okay, the name of this, but this, a value, instead of putting a value in milliamps or microamps or whatever, if we use the curly braces, we can define a parameter. So I'm going to use the parameter I bias, because it's the bias current. All right, that's okay, but if we run that, we need a number. Eventually we need a number, resolve all the way down to a number for this simulation to run, and we'll get an error otherwise. So I add a parameter here, .param I bias equals 10 micros. So now we can do that. We'll see where this parameter comes in handy here in a minute, a few minutes. Same thing, we did the same thing for our compensation capacitor, CC. This CC is the name of the capacitor. It has to start with the C. This parameter, it can be anything, or at least any valid characters. I'm using CC. We don't have a name conflict, but be careful naming things with CC and CC. It's like a data type thing. And it's set to 360 picofarads. So when I do a .op simulation, I'm going to run this, and I just get a bunch of voltages and currents. All right, so this is our list of all device currents, emitter, collector, and base currents, currents through all of my voltage sources, and then all of the node voltages here. We see this N002 somewhere else, and it's 0. It's an internal node somewhere that we don't have labeled. I think it's actually this node right here at the top of the VD source. Doesn't matter for us. Okay, so what we can do in LTspice is you can hover over this, and if I'm hovering over this, you can see in the bottom corner, very bottom, it says right click to edit iBias. You might have to zoom in or something. And it says iBias 9.99999 whatever 7 microamps. Well, of course it is, because I said iBias was 10 microamps. The reason it's 99999 whatever is because 10 micro is a number that's less than 1. And remember, we're using floating point numbers. I don't remember off the top of my head if LTspice is using double precision or single precision floating point numbers. Someone can comment and set me straight. I don't remember. Right now it's not important, but that's like a 0.1. We know that 0.1 can't be represented in binary exactly. In fact, it's not representable. It's an infinite repeat. All right, that's why we get the 999. If I do this and I click and I look at I hover just over my collector node of Q8, you see that it says ICQ8 9.90 something microamps. That's great. Why is it a little less? Well, remember we have base current sneaking out going to the left. If I just hover over this bias N, you see that it's negative 4.46 volts, which is a base emitter voltage of, what is it, 0.56? 0.54 volts, which is fine at 10 microamps. That's the VBE that we would expect to see, especially for 2N3904 at the temperature that we're simulating at. What is the temperature that we're simulating at? How about this? We can go like this. This is my spice error log. I got here by either saying view spice error log or Control L. I did Control L. And if we go down here, we see tnom and temp, nominal temperature, and the temperature that we're simulating it is 27C. Okay, so 27C, our Victor Tango, VT, thermal voltage is 25.87 millivolts, which you can round up to 26 millivolts, but it's not. All right, so 27. LTspice uses 27. PSpice, other simulators sometimes use 25C as your temperature, so watch out for that. Change your temperature with semiconductor stuff, so you know that this is a big deal. All right, next up, those are .op. Going to verify that my node B is 0 volts. I did a little video about this before, so 0, 0, 0, 0. The DC value of VD is 0, VCM is 0. This is a voltage control voltage source with a gain of a half, so we get 0 plus half of 0 is 0. Of course we do. This makes sense because this is in the middle. Power supply VEE is negative 5 volts. Top power supply is plus 5, so right in the middle is 0. Our VE is negative 517 millivolts, so we hover over this, and that also makes sense. It's a little less than our base emitter voltage of Q8 because the collector current, the current through Q1 and Q2, is half of whatever Q5 is, so we would expect a less base emitter voltage here. What's really important to this is just kind of make sure that your node voltages are okay. What we really want, especially for an op-amp, is when you apply a 0 input at the input, differential input, the output should be 0. Okay, actually it should be halfway between the power supplies. Our power supplies are plus and minus 5, so halfway between is 0. This says it's negative 400 millivolts. Okay, that's not perfect, but it is pretty close. Okay, what's super duper important is that Q5 or Q7 and Q6 are both in active mode, forward active mode, which is amplifier mode, as we know. So if this is negative 0.4 volts, the collector emitter voltage here is much greater than the base voltage. So this Q7 is in active mode. It's working like a constant current source or sink. Q6, the PNP, is also in forward active mode, and now we have an amplifier. If, this is an if because it's not necessary for this situation, if we had a DC operating point solution that gave us one of these transistors in saturation mode, or cutoff mode, but it would be saturation mode in this case, any simulations that we do after this, especially the AC simulations, would be bogus. And when I say bogus, I mean bogus. Not valid. Not even worthy of plotting them or even doing the analysis. I know it takes like a second to run the analysis, but it's still a waste of your time. One way that we can make sure that this output node is centered in the right spot at DC for our transistor situation is that makes our small signal model go. But what we can do is we can stick an inductor here, because you remember an inductor has a at DC, especially an ideal inductor is a short circuit at DC. So if I do that, I need to supply a value of this in henries. Let's do a kilo henry, which is an obscenely large inductance, let me tell you. Run the simulation again, and now if we look at out, we see that V out is negative 86 picovolts. I don't think you can see at the very bottom of my screen here, but it's negative 86.13186 picovolts. Do you really believe all that precision? Man, if I change temperature by a teeny amount, it's going to change this voltage by a lot more than that. So it's basically zero for us. All right, I'm going to remove this inductors because we don't need it, but that is a trick sometimes to get a high gain node or high impedance node, which V out is. We look at out and we're looking at DC into a collector and into a collector, and that's it. Makes it very difficult for us to find a proper DC solution, the one that we would expect for an op-amp. All right, so we've already done our .op analysis. I right-clicked on my text block here, and it comes up with this Edit Simulation command window. If you click Cancel, it will show you just the normal text box, which is useful. So I'm going to delete that, and then I'm going to show my DC solution, DC simulation. You'll see why I'm only going from 10 milli, minus 10 milli to plus 10 millivolts in 1 microvolt steps here. Okay, so here we go. We have that. We're going to change VD from negative 10 millivolts to plus 10 millivolts, which you can't see my hands here because I'm just showing my screen. Makes A and B go equal and opposite, but still centered around 0. We can probe that here. Run the simulation. Now I'm going to plot in plus. Okay, goes from minus 10 millivolts to plus 10 millivolts. That's what I wanted. And if I look at in minus, or node B, it goes equal and opposite, and they cross at 0. So I put my cursors up here. I cross at 0. Did you know you can use arrows? Your arrow keys to like step along your simulation points. Remember how I went by 1 microvolt steps, and I'm hitting the left arrow and the right arrow? Howdy doody. Femtovolts, that's funny. All right, let's call that 0. All right, that was boring. I'm going to exit or kill off these. I want to plot just my output node. Oh my goodness. So you see that as the input increases, the output also increases. So we have our signs correct. In plus and in minus are correctly labeled. If we zoom in here, we see that this gain is absolutely humongous. Remember that we did 1 microvolt steps, oops, 1 microvolt steps. Okay, so what we're seeing is we're seeing an actual like simulation result, not just a straight line connecting two simulation points together. If we did 1 millivolt steps, we would see this, but our slope would be wrong. What I want to do here is I'm going to go from, let's say, -5 microvolts. I'll put my second cursor, okay, on, what? Oh, I want both, first and second. Okay, so my first cursor is going to be on -5 microvolts. My second cursor is going to be on +5 microvolts, which, as you know, is a difference of 10. And we span 2 volts in between, or 1.99 volts. And our slope, which would be rise over run, is 199,000. So this is a gain. We call this an incremental DC gain of about 200,000 volts per volt. You would see this in a data sheet as 200 volts per millivolt, which is just same thing. Okay, that's great. That's our DC simulation and op-amp. Now remember that 200,000 is a number that we'll come back to here shortly.